too late. All right, ladies and gentlemen, class recording for today has started. So, yesterday, we started in on the next unit dealing with forces and Newton's laws. And we talked about that forces are the reason why things happen, or the explanation for motions that we see occurring. In the previous unit, we talked about describing motion, talking about its displacement and its velocity and acceleration, but now with forces, we talk about why these things happen. So yesterday, we introduced Newton's first two laws. Newton's first law, summarized up on the board, but we can do that with one word, right? And what's the one word that summarizes the ideas of Newton's first law? Inertia, right? Things don't start or stop moving on their own. An object's motion doesn't change on its own. Whatever it's doing, it wants to continue doing. But things do change. And how much things change are summarized by Newton's second law. And Newton's second law deals with acceleration. And right at the end of class yesterday, we talked about that there are two factors that determine the acceleration of an object. What are the two factors that determine an object's acceleration? Force and mass, right? And it gets nicely summarized, or the effect of all those things gets summarized with this equation right here, F equals ma. Or if we rearrange that equation, A is equal to F over m. So, how does force affect the acceleration of an object? What kind of relationship do they have? It's on page 3 of your packet, like right at the end of, or actually it's page 2, I guess. So force and acceleration are directly related. More force results in more acceleration. And then mass and acceleration are inversely related. More mass means less acceleration, of course, if we keep the other one the same. Okay? So, to summarize those things, let's go here. This practice problem is a concept check, which I think is, where is it? I got it. I think it's on the next page after the, oh, there it is, yeah. All right, so it says, is it possible for an object at rest to have one force acting on it? No. No is the right answer to that question, right? Because forces do what? They cause the object to, let's say, more generally to accelerate, right? Could be speeding up, could be slowing down, could be changing directions, all right? So our answer here, if we only have one force acting on the object, that answer is no. And why? Because forces have acceleration. Now, our forces cause acceleration. Sorry. What we will get into later this week, and actually we'll talk about it today, is the combined effect of several forces. And that's something that we call a net force. And that's going to be an important concept moving forward here. All right? So, let's take a look at this example, which I think, I think it's on the bottom of that page you have it currently on. No, next page? Okay. Next page at the bottom, or on the bottom there. Okay. All right. Sorry, did everybody have a chance to write down the answer to that last question? All right. So it says, Mo, Larry, and Curly push on a 752 kilogram boat that floats next to a dock. They each exert an 80.5 Newton force parallel to the dock. So it says, what is the boat's acceleration if they all push in the same direction? Okay. So, what is this question asking us for? What is the boat's acceleration, right? So for part A, we're trying to find acceleration. Things we know. Mass of the boat. And then, we know force. But in this case, there isn't just one force, there's actually three forces, right? So we have to look at all of those forces, or the combined effect. So we'll call this force of Mo, force of Larry, and force of Curly. All three of them are 80.5 newtons. But when we're looking at a situation where there is more than one force, we can't look at just the effect of one force. We have to look at the combined effect of all of them. All right? And so in this case, well, sorry, I think I skipped something on the front page. No, I believe that. On the very, very front page, when we talked about forces, all right, okay, force is a push or a pull, right? But in the paragraph right underneath where it says force is a push or a pull, forces are vectors, right? And if things that are vectors tell us two things, right? Magnitude and direction. So how hard somebody is pushing or pulling is important, but also which way somebody is pushing or pulling is important as well. In this case, if they all push in the same direction, so what are we going to do with all three of those forces if they're all in the same direction? We're just going to add them all up, all right? So the combined effect of all three of these forces, if my math is right, is 241.5. Okay? And now we know the total amount of force that is acting on that boat. If we now know the total force that is acting on the boat and the mass of the boat, we can figure out the acceleration using Newton's second law. Right? So F equals ma. And we know that the force in this case is 241.5. The mass, 752. And it should be something a little less than 0.33. When you have your calculator out, go ahead. So, or Claire, did you do it right? So 0.321, 461. 1436. Are there two ones in there? Is that what I? Yeah. Okay. So are we writing all of these numbers down here? We shouldn't, right? Rounding significant digits. This is 4 significant digits. This is 3 significant digits. We always round to the lowest number, right? So we should round this number here to 0.321. And then because it's acceleration, what unit will it have on it? Meters per second squared. Good with that idea? Okay. So before we do part B, let's update Newton's second law. All right? So when we have multiple forces acting on an object, we have to look at the combined effect of all of those forces. And the combined effect of all of those forces, right, the sum of all forces, we refer to as the net force. Okay? The Greek letter sigma, that's the sideways M, okay, is what we use to represent the sum or the total of something. So when we throw the Greek letter sigma out in front of F, that means not just force, but the net force, the combined effect of all of the forces that are acting on the object. So if we want to determine the acceleration of an object, we can't just look at one force, we have to look at the combined effect of all of them. All right? Does that make sense? Are we okay with that? Okay. Going back to this problem here, okay, duplicate this, and then get rid of all this writing here. Right? If we look at part B, it says, what is the boat's acceleration if Larry and Curly push in the opposite direction of Mo? So in this case here, for part B, it's asking us for acceleration. So, boat's acceleration is still asking you for acceleration. The mass of the boat hasn't changed. That's still 752. But now in this case, we still have three forces, right? We have force of Mo, force of Larry, force of Curly, right? They're all still pushing at 80.5 newtons. But it tells us there's a direction change here, right? It says that Larry and Curly push in the opposite direction of Mo. How do we represent something that's going in the opposite direction? Negative sign, right? So here, we would represent Mo's force as positive, but Larry and Curly's forces would both be negative. The net force idea says we're summing all the forces. And that's true. We always add all of the forces up. It's just in this case, we're adding some negative numbers, right? So when we look at the combined effect of all three of these, we end up with negative 80.5. Does that make sense? That negative 80.5, that would be our net force, sigma F. And Newton's second law tells us that sigma F is equal to m times A, right? This is our net force. The mass still doesn't change. It's 752. So now we can solve for our acceleration. All right? We'll go ahead and give me a number there so I have something to write down. Did you already put it? Give me one more number, Claire, right? This is 3, and this is 3.
It's 107.
Let's go with that. All right. Question. Let's interpret our answer here, right? We got a negative acceleration. We kind of talked about negative acceleration in the previous chapter, and in a lot of cases, negative acceleration means what's happening to the boat. A lot of times, negative acceleration has that connotation that we're slowing down, okay? But it's really just a directional thing. In this case, the boat is sitting there. It's not moving. It now experiences a negative acceleration. Clearly, it's not slowing down. It was sitting still to begin with. So, if it is sitting still and it experiences a negative acceleration, what's going to start happening to that boat? It's going to start moving backwards. It's going to actually be speeding up. Even though it has a negative acceleration, it's just speeding up in that negative direction. Negative acceleration means slowing down if we're already moving in the positive direction. Here, because it's sitting still, negative acceleration actually causes that object to speed up, just speeding up backwards. Is that okay? Are we okay with interpreting that answer? Does that work? Okay. All right. Good with Newton's second law. Do we understand the relationships there, force, mass, and acceleration? Newton's second law we're going to use a lot in this unit and then as we continue moving forward. So we'll have many more chances to look at the relationships there. Yeah? All right, so Newton's first law, inertia. Newton's second law, acceleration and the factors that affect it. Newton's third law is a little bit different. Newton's third law doesn't deal with what is happening to a single object. It deals with the interaction between two objects. And so it says here, Newton's third law describes the force that objects exert on one another. Key points. For every action force acting on an object, there is a reaction force acting on a different object. The action and reaction forces are equal in magnitude, opposite in direction. Again, probably something you've heard before, all right? But what does it mean? Oh, not that one. Where is it? Oh, I thought I The end result of this, Newton's first law is inertia. Newton's second law is acceleration. Newton's third law, forces come in pairs. There is no such thing as a single force. Forces always have a pair. And if you look over at the side of your sheets, right, there's a couple of pictures there. Okay? Here there's a guy pushing on the refrigerator. Now, if the guy pushes on the refrigerator, Newton's third law says the refrigerator pushes back on him. Okay? Here, this picture, gravity from the Earth acts on the space shuttle to keep it in orbit, but gravity from the space shuttle acts on the Earth. All forces have a pair out there. All right? In this case here, right, person pushes on this little object, moves it forward, but there's a force on the person that moves backwards. This one's hard to see sometimes because it's pretty easy to see. If I take this book and push it, it moves. But if it's pushing back on me, what should I do? I should move too, but I don't. Right? One thing that gets lost sometimes in Newton's third law is the idea that, yes, those forces come in pairs, but sometimes that reaction force, the thing that's coming back on the person that's giving the force, is not the only force that's acting on that person, right? I push on this book and it pushes on me, and that's true. But there's also some friction between me and the floor, and that's why I don't start moving backwards. Sometimes it's hard to isolate those action-reaction pairs to show that they're actually pushing on each other. All right? Does that make sense? We okay with that? All right. We'll look at more of that too as we go along here and look at some examples. So let's take a look at this part right here, guided example 5.5, tippy canoe. So it says two groups of canoeists. In the past, I've had a debate with my class, not debate, we've had a discussion, if that's actually the plural form of a person that rides in a canoe, or people that, canoeists, I'm not sure. So, the plural of canoeist has never come up in my normal everyday conversation before, so I don't really know. It says, after a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is 150 kilograms. The mass of canoe 2 and its occupants is 250 kilograms. What is the acceleration of each canoe? All right? So, those are our unknowns, right? It tells us that the mass of canoe 1 is 150 kilograms. The mass of canoe 2 is 250 kilograms. And then it says canoe 1 pushes on canoe 2 with a force of 46 newtons. So that means that canoe 2 feels a force of 46 newtons. But according to Newton's third law, if canoe 2 feels a force of 46 newtons, what automatically has to happen? Canoe 1 feels the same force, but which way? Negative, right? So, that means the force on canoe 1 is negative 46 newtons. Does that make sense? Look at that. Here, we would see this interaction. We would actually see canoe 1 move backwards when it pushes on canoe 2 because the water reduces that sort of resistance force that maybe friction is causing, right? So you could actually see that, right? If you've ever been, if you're like done bumper boats or in inner tubes or things like that, right? If you're messing around with somebody and you push them, you actually end up moving backwards, right? So now, we've used Newton's third law to show that the forces on each object are equal but opposite. But now we can use Newton's second law to calculate the acceleration of each canoe individually. Okay? So, we apply Newton's second law to each canoe individually. We know the force that's acting on each canoe. We know the mass of each canoe, so we can figure out the acceleration of each canoe individually. All right? So go ahead and do that real quick. Good with those two numbers right there? Alright, so real quick, the next question is sort of a conceptual question to follow up on this one. Okay? Let's say, in the follow-up question, canoe 2 was replaced with a big, huge tanker. Right? Most of us would probably see, right, that canoe 2 or canoe 1, when it pushes on the tanker, it moves backwards, right? It does. That doesn't mean that the big, huge tanker doesn't feel that force. But once we've established Newton's third law, that the forces are equal and opposite, right? This bottom purple circle down here, now it becomes a Newton's second law problem. We use Newton's third law to figure out how much force each object feels, but then we use Newton's second law to individually calculate their accelerations. If canoe 1 pushes on the big, huge tanker ship, right? They would both feel the same force, and that's Newton's third law. But now, individually, we use Newton's second law to find their accelerations. We talked earlier, right? How does mass affect the acceleration of an object? Inversely. So if this tanker ship, 25,000 kilograms, it has a way bigger mass than the canoe that originally pushed the force, or that originally applied the force. So if its mass is way big, what are we going to see about its acceleration? Real small, right? Mass doesn't determine if something moves. It determines how much it moves. Okay? So keep that in mind. Just because something is really, really heavy doesn't mean that it doesn't accelerate. Its acceleration is just so small that we might not notice it. Okay? Good there? We're okay with that idea? All right. Tomorrow, in class, we will do a couple of example problems summarizing Newton's laws, and then we'll start getting into applications of Newton's second law, because that's what the whole second part of this section is about, is application of Newton's second law, finding net force and all that fun stuff, right? So that is our plan for tomorrow, all right? Oh, now that we are two separate classes, or we will be in the very near future, I will start updating your guys' calendar on a more regular basis, and that will include like some homework assignments and things that reinforce stuff we've done in class. I won't, as we've talked about, I don't really collect the homework, but it's stuff that could help you reinforce what we've done in class. Also, I'll be a little bit better maybe about giving you guys some interim evaluations, like giving you little quizzes to see if we're keeping up on things. So it's not just boom, test at the end, here it is, know whether you don't know it. So keep an eye out for those things as now I can talk to you with you guys every single day and do things with